Okay, so I think we have started with the codec section, and we need to cover some basic mathematics so that you can understand uh, how to do encoding and decoding. So we are looking at encoding and decoding portion. Essentially, certain basics of coding theory. So in a very simple, channel. So when we are looking at bits, we can actually encode them in this repetition code. Uh, each bit is repeated 3 times. So 1 is repeated 3 times and 0 is repeated 3 times. And this code can detect and correct errors. So actually, as you have seen here, uh, if I want to correct single bit flip, here I have to basically use 3 bits rather than single bit. And if I want to correct 2 bits, I have to take 5 bits. The repetition should be 5 times and so on. So this actually depends on what is known as Hamming distance of the code. So it is defined as, so distance between x comma y. If x and y are two vectors of say length n, so Hamming distance is number of places they differ. So for example here, distance between this and this is 3. So essentially this code has distance 3. Okay. And the top code has distance 5. And there is a result which says that the middle distance is d. So if the distance of the code is d, it can detect d minus 1 errors and it can correct d minus 1 by 2 errors. Okay. So here, for example, if code has distance 3, so 3 minus 1 by 2 is 1. So you can correct 1 error. Whereas in that case, d is equal to 5. You can see that the number of bits they differ is 5. In fact, we are looking at minimum Hamming distance among all code words. So there it can correct 5 minus 1 by 2, which is 2 errors. Okay. So this criteria of the Hamming distance is useful for this simple techniques. There is also a probabilistic version of this, which I am going to explain in the next slide, that how you can actually, the probabilities calculation is also similar to whatever correction we are doing through this Hamming distance calculations. So the Hamming distance calculations are basically, so what we are doing actually, once we are sending some vector from this set and we receive something, we just look at what is known as maximum likelihood decoding, right? So we basically see in terms of computing the distance from this receipt vector with whatever vector was there and see which one has the smallest distance, right? So in this case, 110 was the smallest distance, right? So that is what. Now, if you look at this code and this binary symmetric channel, so you can see that if you send bit 0, you will receive bit 1 with probability of error p. Similarly, if you send 1, you will receive 0 with probability of error p. And if you send 0 and receive 0, the probability is 1 minus p. Similarly, if you send 1 and you receive 1, right? So this is the binary symmetric channel, very popular channel. Now, in this channel, I can show you by just computing the probabilities. Actually, you can see how this repetition code is useful for error correction. So in general, we assume, we know that the probability is between 0 and 1, but here we assume that the probability lies between 0 and half. If not, you can switch the value because it's a binary symmetric channel. So, but just for the understanding, so we are assuming just without loss of generality, suppose probability is between 0 and half. Okay. And now, suppose receive vector is 110. So we know that because either vector that was sent was 0, 0, 0 or vector it was 1, 1, 1, received is 1, 1, 0. So I can compute these probabilities. Probability that 1, 1, 0 is received and 0, 0, 0 is sent is nothing but each individual product of each probability of each individual thing, right? So probability that 1 was sent and 0 was received at this position. 1 was sent, sorry, 1 is received, 0 is sent, 0 is received and 0 is sent, right? So this is how the whole probability will be. Probability of 1 is received, 0 is sent, times probability of 1 is received, 0 is sent, times probability of 0 is received and 0 is sent. Okay, this whole thing. And now you can see that if suppose probability is 0.05, you can compute this value is 0.002375. Right. So essentially, once we receive 110, I can actually, so the probability of 000 sent is this. Similarly, I can compute the other probability. So if 110 is received, what is the probability that 111 was sent? I can compute again using similar technique. It turns out that this probability is this. Now you can clearly see that this probability is bigger than the other one. So that's why that means more likely that 111 is sent rather than 000. Okay, so this is how the, any question at this point? Huh? This is a very simple probabilistic decoding, right? So this is equivalent to whatever we are doing in the distance part. Okay. Now, I think you have done this course on discrete mathematics. Probably you remember something about fields, right? So fields are important construct, as you know that all your data packets are nothing but fields. So, you know, I can now build some machinery. So this is a very simple scenario what I explained to you. But actually, in real calculations, we want to minimize this repetition, right? We want clever techniques of error correction. How do we do, you know, error correction? So now this channel will be very, very different. Actually, in the case of DNA storage, the channel will be very, very different. Actually, we will see that new kind of channel. So new kind of, you know, error correcting codes will be required, especially. So here, this is very simple. The bit flip. Bit flip is the very simplest channel actually. But so let me collect some of the basic things here. So we know that Zn is a field if and only if n is a prime number, right? You remember? This is something. So Z2 is a field, Z3 is a field, Z4 is not a field, Z5 is a field, Z6 is not a field, and so on. I hope you remember this fact. I'm going to, you know, so in general, we have field with q number of elements, which is having 0, 1, alpha, alpha square, and so on. Alpha raised to power q minus 2, right? Wait, what is alpha? Alpha is a root of a polynomial which has no root in the ground field, right? So this we can construct from integer modulo p. So alpha is a root of a polynomial fx, and those kind of things are there. I think you remember that machinery, but anyway. So essentially, the code that we just saw, C is equal to 0, 0, 0. I'm just keeping ourselves to the case of binary. So here, this is nothing but subspace of Z2 raised to power 3. So let me, what does that mean? Subspace means, you must have done a course on linear algebra, right? So vector space, subspaces, right? You must be remembering, right? I think have you seen any finite? So let us take a very simple example. So let us take R square. R square is what? R cross R. R is a real line, and you take the cross product, you get a plane R square. How many one-dimensional subspaces are there of R square? So basically, geometrically, if you want to think, take the plane, and if you take any line passing through origin, that will work as a subspace, one-dimensional subspace. Any line passing through origin. How many lines are passing through origin in R square? Infinitely many, right? There's so many directions. Any direction you draw a line passing through origin, that will be a one-dimensional subspace, right? So this is the idea of subspace. Now, if you change field from infinite to finite, suppose for simplicity we take binary field Z2, integer modulo 2. So in that case, if I take a space Z2 raised to power 3, so first of all, how many vectors will be there in Z2 raised to power 3? 8 vectors will be there, right? 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on up to 1, 1, 1, right? All 8 vectors will be there. Now, if I ask, in fact, how many one-dimensional subspaces will be there now? Can you give me an answer now? There are, so this space is of 3 dimension, right? Dimension of this vector space Z2 raised to power 3 is 3, because there are 3 basis elements 1, 0, 0, 0, 1, 0, 0, 0, right? So 0, 0, 1, 0, 1, 0, sorry, 1, 0, 0, 0, 1, 0, 0, 0, 1, right? So these are 3 natural bases, right? Let me show you briefly about this. Zero 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 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 1. Do you have all 8 vectors here? I mean, you can. Another one will be R cube. So R cube is a 3-dimensional, I am just comparing here. Okay. R cube is our 3-dimensional space X, Y, Z, such that X, Y, Z belongs to R. That's a 3-dimensional space, infinite space. This is finite space. Now, if I ask how many one-dimensional subspaces are there, if I take any non-zero vector here, right, and take it as a basis, it will give us a one-dimensional subspace, right? Because I can say that so basically, if I take 0, 0, 1, so basically if I take the vector 0, 0, 1, okay, this will, sorry, 0, 0, 1, this is nothing but 0, 0, 0, 0, 0, 1. This is our one-dimensional subspace, right? Okay, take the another vector 0, 1, 0. So this is 0, 0, 0, 0, 1, 0. Okay. Next 1, 0, 0. These are all one-dimensional subspace, right? So how many of them are there now? 7. So we can count subspaces, right? There are 7 of them. I can take any non-zero vector here, except the first 0, 0, 0 vector, right? So basically, our code C which we use in the repetition code, there are only two vectors, 0, 0, 0, 1, 1, 1. 0, 0, 0, 1, 1, 1 is one-dimensional subspace, right? Actually, it is the last one, 1, 1, 1, right? So it is a subspace of this whole space. Essentially, our code that we use to correct errors is nothing but, mathematically, it is nothing but a subspace of some dimension. Okay? And here it is dimension 1. Why? Because the generator matrix has only one element, right? The basis has only one element, which is 1, 1, 1, right? 1, 1, 1 if I take, and so I think I can generate all of this like this. If I say 1, 1, 1, essentially that means lambda times 1, 1, 1, such that lambda belongs to Z2, right? So there are two possibilities, 0 or 1. So we are basically getting 0, 0, 0, 1, 1, 1. So one-dimensional subspace. So our code that we used was one-dimensional subspace, right? So basically, 1 minute. How many two-dimensional subspaces are possible, by the way? Two dimensionals, I can take any two linearly independent vectors. So if I take say 0, 1, 0, 1, 0, 0, this is one two-dimensional subspace, right? If I take 1, 0, 0, 1, 1, 0, this is another two-dimensional subspace, right? So how many such two-dimensional subspaces are possible? You can count, right? I mean, if you take two vectors which are linearly independent, means lambda 1 times first vector plus lambda 2 times second vector equal to 0. I mean, if this implies that lambda 1 and lambda 2 is equal to 0. In other words, so two vectors are linearly independent if one is not a multiple of the other with the scalar lambda. So here lambda is in the Z2. Okay. Any question at this point for this? I'm just collecting your linear algebra thing. It's all linear algebra. और अगर फिर से पूरा linear algebra पढ़ाना पड़ेगा तो बहुत ज़्यादा हो जाएगा, right? But there I think in linear algebra you might have only seen reals or complex, right? Here you can touch and feel. Yes. Question? Feel. So field basically, I am taking a very simple example of a field which is integer modulo n when n is a prime number. Field means what? You made two tables, right? Addition and multiplication, if you remember. In addition table, what happens? Every element has an inverse with respect to addition. And in case of multiplication table, every non-zero element has an inverse. That there are two important things, right? Field means every element has an inverse with respect to multiplication as well, right? Z4 is not a field because 2 into 2 is equal to 0, none of them is 0. Remember? Field is an important thing. So binary field I am considering, I am not looking at even the ternary field or whatever, those kind of things, but only binary field, right? So it's something very simple. The only thing is that here the subspaces are over this binary field. Z2 is the smallest field. I am taking 3 copies of Z2, Z2 cross Z2 cross Z2 will give you Z2 cube having 8 elements. This is our full space. Just like analogous to R cube. This is Z2 cube. Here there are infinitely many points in R cube, but here there are only finitely many points, right? Only 8 of them, right? So in the plane Z2 square, how many points will be there? 4 only, right? 0, 0, 0, 1, 1, 0, 1, 1, right? Only 4 elements. So discrete means you can touch and feel. Real complex means, you just in the air, right? I mean, here you can touch and feel everything. You can count how many subspaces. And this linear algebra is what is used a lot in error correction. Okay, for error correction, yes. Yeah, so we need to find a basis. So basically, if you look at, I can, if you see here, a subspace basically if V is a vector space, if you remember, so here we are saying that Z2, n, suppose we take Z2n, right? So this is all vectors of the form x1, x2, xn, such that xi belongs to Z2, right? How many elements will be there? 2 raised to power n in this whole space. Now, I have to find a basis. So basis is nothing but consisting of it. So there are, a set of vectors here will be basis like 1, 0, 0, 0, 0, 1, 0, 0, 0, 0. These are n vectors will be there. Now they act as a basis because there are two conditions. Number one, all these vectors are linearly independent. Right? This property is true. Linearly independent means if I take, so basically I can call it say E1, I can call these vectors as E1, En. En. Right? So these are the vectors E1, E2, En. That means summation lambda I Ei is equal to 0 will imply that lambda I is equal to 0 for every I. So these vectors are linearly independent. That is first condition. All these n vectors are linearly independent, right? And they span the whole space. So span of E1, E2, En is the whole space Z2n. Span means if you take any vector in Z2n, it can be written as a linear combination of these vectors, the basis vectors. Right? So if I take, so for example, in this here, if I take any vector, say if I take 0, 1, 1. So 0, so first of all, what is the basis here? So basis here is, you can see that basis here is first vector E1 is 1, 0, 0, E2 is 0, 1, 0, and E3 is 0, 0, 1. Three vectors are basis in Z2Q. Now, if you can see that I take any vector here. First of all, these vectors are linearly independent. Lambda 1 times this plus lambda 2 times this plus lambda 3 times this is equal to 0 means all scalars are 0, right? These vectors are linearly independent. Second, if I take any vector, say suppose I take 0, 1, 1, this can be written as linear combination of these vectors or not, right? 0, 1, 1 will be 0 times E1 plus 1 times E2 plus 1 times E3, right? So every vector in the space can be written as a linear combination of these vectors, right? So that means they span, right, the whole space, right? So these two conditions should be satisfied. Then we say that it's a basis, right? Got it? I'm just recalling linear algebra in a finite flavor, right? Okay. So this is what it is, basis. So essentially what I was saying that now this space that we use for error correction, you saw this vector, these two vectors we use repetition code, right? This code is nothing but a one-dimensional subspace of the whole space. Why it is one-dimensional? Because it is generated by 1, 1, 1, right? Why 1, 1, 1? Because lambda times 1, 1, 1 gives you all these, both the two vectors. But lambda is a scalar in the ground field. Any question? Huh? So linear subspace means, so basically if you are taking two elements in the subspace, right, and they're taking linear combination, which is also in the space itself. Closed with respect to the linearity, right? Two vectors. Space, because here we are talking about vectors. These are the subspaces, right? Also in the space. No. So basically, which one is, if you're looking at Z2 raised to a whole, Z2 raised to power 3, all, you take any two vectors. So basically, combination means what? Because scalars are either 0 or 1. If you take lambda 1 times this plus lambda 2 times this, what will happen actually? Suppose we take these two vectors. First of all, I mean, so, and I want to ask what space they are going to generate. So 110 and 101, both these vectors are linearly independent. First of all, you need to check that. If yes, then what we can do, lambda 1 times this plus lambda 2 times this. Where lambda 1 and lambda 2 in Z2 will give you 4 vectors, right? Will give you 0, 0, 0, 1, 1, 0, 1, 0, 1, and 0, 1, 1. These 4 vectors you will get, which is nothing but two-dimensional subspace of the Z2 3. Yeah. Basis. If you are looking at basis, the vector should be linearly independent, number one condition, and then the span should be there, right? So all I'm doing is an example. Nothing. I'm not doing any theory. All that, conditions. Nothing. This is how the linear algebra should be taught, actually, right? Through examples. Okay. So you can clearly see that. So now you can count how many one-dimensional subspace. The question is actually very interesting. You see, in order to correct single bit flip, I have used this code 000111, right? So question is, are there any other? Now you can see that there are 7 more one-dimensional subspaces which I could have used, right? So the question is, which one is efficient, right, for corrections? And that gives you most challenging coding theory problem, that out of, this is a small case, but in general, if you have n-dimensional space, and I have to look at k-dimensional subspaces, there are many. And some of them will be very good for error correction, some of them may not be very good for error correction. So our job is to find good error correcting codes. This is what is the challenge. Okay. Here I have shown you only one example, right? I'm just showing you one example, but in general, the problem is like this: finding a good error correcting code. I think you can ask questions. Any question here, right? I mean, or you are able to recall some linear algebra. Hmm? 1, 0, 0 and two linearly independent, two-dimensional subspace. Yeah, you can use any. You can use, so two-dimensional. So basically, okay. One thing I should tell you here, because we have used 000111 because we had only single bit. If you have 2 bits to encode, then we require two-dimensional space. If you have 3 bits, so here because we had only single bit, that's why we have used one-dimensional subspace. Okay, that depends on how many. So let me show you those some of those calculations. So this is the very general setup. You can see that FQN is a whole space. I've given you example of Z2 raised to power n, which is a binary. Here it is, if FQ is a field with Q number of elements, this is the whole space. A linear code is nothing but a k-dimensional subspace of whole n-dimensional space. In our specific example, k was 1 because we are looking at one-dimensional subspace, right? So basically what happens, suppose we have k bits. K bits are there. So we know that every vector space, every subspace actually, because C is a k dimension, there will be basis having k number of elements, right? Basis having size of basis will be k elements. K vectors will be there. Those k vectors I can put it in the form of a generator matrix, and I can multiply k bits with that generator matrix, which is k by n. So basically, k bits are encoded into n bits. using this generator matrix, So let me show you. For example, here we had C as 0, 0, 0, 1, 1, 1. So generator matrix is 1 cross 3. K is equal to 1 here, right? And N is equal to 3 here. So we are having one bit 0. If I want to encode Z0, I will multiply with here G. This is 0 times 1, 1, 1 will give us 0, 0, 0. And 1 times G is nothing but 1 times 1, 1, 1 will give us 1, 1, 1. So you see, this is 1 cross 1. And this is 1 cross 3. So you will get 1 cross 3. See? So in general, if we have k vectors, x1, x2, k bits, if we have k bits, I multiply with G, which is k cross n, and I will get a vector. I can call it, say, y1, y2, yn. N bits. Using G. So k bit vector multiplied with the generator matrix, which is of size k cross n. K rows, n columns. What is this G? G consisting of basis elements of the vector space that we are using, right? K-dimensional subspace, yes. K-dimensional subspace. So I'm just taking all the basis elements, putting them in the form of a matrix, because all these vectors will be linearly independent anyway, right? So K rows in columns. So take K bits, multiply with G, and you get N bits. Take another, whatever K bits. So you carry this, right? So here we have taken, whether it is 0 or 1, we know. So 0 is encoded as 0, 0, 0, 1 is encoded as 1, 1, 1, right? This is what it is. So in general, if there are k bits, multiply with k by n, we get y1, y2, yn. So n bits. K bits are mapped into n bits using this subspace. Okay. So code is nothing but a k-dimensional subspace. A linear code is nothing but a k-dimensional subspace of the whole n-dimension space, right? This is what it is. Yeah, so basically, first of all, if there is an n-dimensional space, and if you are looking at k-dimensional subspace, one question that you can ask, how many k-dimensional subspaces are there? Because here you can count. I have shown you for n is equal to 3, there are 7 one-dimensional subspaces, right? All non-zero vector. If you take any non-zero vector, you will get one-dimensional subspace, right? Right. So the general formula is what? That's a good T time problem, but yeah, it's not easy. It's a formula which we call it as a Gaussian binomial coefficient, n by k over q. So which is of something like q raised to power n minus 1 into q raised to power n minus q into q raised to power n minus q square, and so on, divided by, another expression. It's a beautiful counting argument, actually. If you have done a course on discrete math, so it's not a, so it's a good T time problem. Very good. I mean, yeah, so we can ask this exam also, right? So how many k-dimensional subspaces are there of a n-dimensional vector space? Here, over a finite field having q number of elements, right? So this is a beautiful thing, right? I showed you an example. For n is equal to 3 and k is equal to 1, there are 7. So the first non-trivial case will be, if I ask you, there is a three-dimensional vector space, how many two-dimensional subspaces are possible? So you need to just choose 2 vectors out of those 8 vectors. You have to choose 2 vectors which are linearly independent, right? And just make sure that how many ways you can choose, right? 2 linearly independent vectors, right? Each 2 linearly independent vectors will give you, and just make sure that you're not getting the same set of vectors. So you have to avoid certain. So you have to divide. That's why there is a division formula, right? So first count how many and divided by the repetitions. So you will get total number of k-dimensional subspaces. Yes. 0, 0, 0 will not be in a basis, right? Because a singleton zero vector is always linearly dependent. So the first condition for a vector to be linearly independent is the vector should be non-zero, right? So if it is 0 means lambda times that vector 0 is always 0, no matter what lambda you take, right? This is all brush up of your linear algebra course, right? But over beautiful flavor of finite fields. So how many subspaces? This is a good question. तो एग्जाम के लिए क्वेश्चन तो मिल गया, right? So I should tell you how to approach this problem. First of all, think like this. You are filling a matrix. So basically, suppose very simple, if I ask you how many bases are possible for a k-dimensional vector space? How many bases are possible? That's another counting problem. So we know if you take any k linearly independent vectors, it will give you a basis, right? Suppose we are looking at the binary vector space. So over Z2 raised to power n, how many k-dimensional bases are possible, right? So the question is, you have to choose those. So first vector can be chosen in 2 raised to power k minus 1 ways. Any non-zero vector. First linearly independent vector can be chosen in that manner. Second vector, so once you have chosen the first vector, second vector can be chosen in 2 raised to power k minus 2 ways. Why? Because once you have chosen the first vector, if you multiply with lambda, you get the second vector. And lambda is having two choices, 0 or 1, right, in case of binary. So first vector could be dependent on the other vector in 2 ways. Total number of ways of choosing the vector is 2 raised to power k. And you have to subtract 2 ways. So 2 raised to power k minus 2 is the second. The second vector can be chosen in 2 raised to power k minus 2 ways. See? Third vector can be chosen in 2 raised to power k minus 2 square. And so on. This is how you have to develop the counting argument. And the similar argument, actually, you have to do it for general when you compare subspaces. How many k-dimensional subspaces will be there? I showed you, I gave you an idea or hint how to approach counting how many bases will be there. Right? This is all mathematics, not in competitive programming. Okay? But yeah, so this is the challenge. There are so many subspaces. Which one is good for error correction? You need to find. It's a very difficult problem. It's a very, very difficult problem. So there are different ways of constructing codes and so on and so forth that you will see. Okay, so now I think I'll show you. So a code is nothing but a linear code is nothing but a k-dimensional subspace of the whole space. FQN is all those n tuples over FQ. What is FQ? FQ is a field with Q number of elements, finite field, which is defined in the form of 0, 1, alpha, alpha square, and so on. Your discrete math, maybe first, second, third lecture, if you are able to recall, 2 साल हो गए वो बिल्कुल भूल गए होगे, right? So, but that is what it is, right? So, and we define what is known as D of C, minimum Hamming distance. So it's the minimum of Hamming distance between all code words. So basically, elements of this C are known as code words. Like 0, 0, 0, 1, 1, 1, both of them are known as code words, right? And we compute the distance between all of them. Right? Whenever you just compute the distance, pairwise distance. If C is a k-dimensional subspace, write down all vectors, all code words, and compute the Hamming distance pairwise between each of them, and take the minimum. That is nothing but the minimum Hamming distance. Okay. So if minimum Hamming distance is D, you can correct D minus 1 by 2 errors. This is the main result of coding theory. So here is C is a NKD code, N is length, K is known as dimension. So basically each error correcting code is defined by 3 parameters. N, which is length. In our previous example, N was 3. 1110008. N was 3. K was the dimension. There the dimension was 1. K is equal to 1. D is the minimum Hamming distance. I just gave you the formula of minimum Hamming distance, right? You compute the Hamming distance pairwise among all vectors and take the minimum, right? And each code can be described by a generator matrix consisting of basis element of the, right? So, for example, in the case of 000111, the generator matrix was 111 only, consisting of one vector, right? So, in general, it has identity matrix Ik times a matrix A. K rows, N columns. This is known as generator matrix. You take K bits, multiply with G, you get N bits. This is how you do the encoding. So, encoding of bits is done through this multiplication by this matrix G, known as generator matrix, right? Another important thing, we can describe dual code. I think you must have heard about dual vector space also, right? You know, remember? Linear bilogical साफ हो गया होगा. Dual space is what? If V is a vector space, dual of V is what? All those vectors which are orthogonal to the vector. So if you basically, we are looking at C per. If C is our k-dimensional subspace, right? All those vectors y in FQN such that inner product between x comma y is equal to 0 for every x in C. C के हर एक vectors corresponding, we are finding which are the vectors in the space which are orthogonal, and we are collecting them. That space is known as dual code, and it is known that dimension of C perp is n minus k. Must have heard about rank nullity theorem, सुना था ना? Rank nullity theorem. सुना से लग रहा है? Dimension of C plus dimension of C perp is equal to dimension of the whole space. That is a beautiful result. Dimension of C plus dimension of C perp is equal to dimension of the whole space, which is n. Right? You remember that result? So basically, that is what is a dual code. Huh? Yeah. H is separate. I am going to tell you about H. H is a separate thing. So basically, I should tell you that you can think of H as a generator matrix of the dual code C perp. And H is a matrix which is orthogonal to G. So GH transpose is equal to 0. That is how it is. It's a dual connection actually. Okay. So if G is IK bar A, H is minus A transpose I n minus K. So rank of H is n minus K, whereas rank of G is K. Rank of G is K, rank of H is n minus K. So it is, in other words, we also call null space of, I think let me give you an example. Example ज़्यादा better, right? But at least, yeah, I'm not going to do again the whole theory of linear algebra over finite fields and whatever this. But if you want, more and more things are given in your the course on coding theory which is available. But anyway, so look at this. So now if we take G to be 10110101, you can do it by hand. 10110101. 2 rows, 4 columns, and we are looking at the binary space. How many vectors will be there in C? If generator matrix has 2 vectors, First vector is 1, 0, 1, 1. Second vector is 0, 1, 0, 1. Code will have how many vectors? 4, right? First, you can look at the first column here, the first row here. 0, 0, 0, 0 is the first vector. 1, 0, 1, 1 is the second vector. 0, 1, 0, 1, third vector. 1, 1, 1, 0 is the fourth vector, right? All the 4 vectors. How do we get these 4 vectors? It's very simple, right? Lambda 1 times this G1 first plus lambda 2 times second, right? Where lambda i's are in Z2, lambda 1 and lambda 2 in Z2, 0 or 1. So if you just run lambda i's, you get these 4 vectors, correct? It's a 2-dimensional subspace. Yeah. No, it's just some, I'm taking just 2 vectors, that's all. H तो अभी हम बताएंगे. I'm not. H we'll talk about. First of all, you see that from G we are getting this C. Is that okay? Huh? This C is okay. This C is okay. By taking 2 vectors, so I'm calling them G1, G2 as a generator matrix, and I'm now getting all these 4 vectors. Right. So first, once we have this code, what are the parameters? What is length here? 4. N is equal to 4. So C, I have written C, 4. Dimension 2. There are 2 vectors in the basis. So K is equal to 2 there. And distance is how much? Distance, if you compute, distance between this and this is what? 3. Between this and this is what? But distance between these 2 vectors is how much? 3. Between these 2? 2. Right. And then maybe 3. What about this and this? 2. So all pairwise distance you can compute and then take the minimum. So D is equal to 2. So 4, 2, 2 is the parameters of this code. 4 is length. Okay? N is equal to 4 is length. K is equal to 2 is dimension. And D is equal to 2 is the distance, right? Okay, now he's asking how do we find H, right? So what is G? If you look at this, I am just applying this formula. If G is this, IK bar A for some matrix A, I don't know what it is, right? Something. So from if G is of this form, this is the standard form of G, H is of this form, minus A transpose bar IN minus K. Okay? In our example, N is 4, K is 2. So N minus K is what? 2. So this matrix will be I2. And then minus A transpose. Whatever is here, take minus of it and take the transpose. Minus 1 is same thing as plus 1 because it's modulo 2, Z2. So we are actually left with A transpose. Right? So here we get, see that is there. 1 0 1 0 1 1 0 1. So see the last 2 columns are I2 1 0 0 1. Got it? I'm just applying that formula. So once we have this, okay, so then I can, maybe next time I can explain to you how do we correct errors in using another approach known as Codec decoding, right? Okay. So That we will see in the next class.